Hi, my name is Talia, and I'm a high school senior who loves teaching others chemistry and math. This YouTube channel is a supplemental resource to anyone who may be having difficulty in their chemistry classes and who wants just an extra boost of knowledge when learning new skills. This week, I'm going to be talking about VSEPR diagrams, but I'm only going to be discussing them at the Honors Chem level, which means there are some diagrams I'm not going to be including and that I will include later when I make an AP chemistry version of this entire unit. So please understand that if you're in AP Chem, these are only some of the diagrams you will have to know. I hope you enjoyed this video, and without further ado, let's get started.
Okay, so we are going to get started with the different VSEPR diagrams, and just an intro. VSEPR theory, it stands for valence shell electron pair repulsion theory, and it basically shows the three-dimensional shape of a molecule based on how many atoms are bonded to the central atom, as well as the number of lone pairs on the central atom. So we learned that atoms can make bonds in order to form compounds. We also learned that those bonds can be polar or non-polar. And with VSEPR, we kind of combine everything together to make 3D diagrams of different compounds and determine if those compounds themselves are polar or non-polar. So these VSEPR shapes I'm going to talk about are at the Honors Chem level. There are like 4 extra ones that are for AP Chem. And like with some of the other videos I've made, I'm going to make an AP Chem version of them later. So let's first start with the linear VSEPR model. My example here is carbon dioxide. This is also not my chart. I got it from my Honors Chem teacher, Sarah Lippitz. So I'm going to draw the Lewis structure for carbon dioxide. So we have carbon and 2 oxygens. Oxygen has 6 valence electrons. Carbon has 4, and I'm going to, for single bond, each oxygen to a carbon, and then I need to double bond each oxygen to the carbon in order to have 8 electrons for all 3 atoms. So now my Lewis structure looks like this, with 2 lone pairs on each oxygen. So this is the linear VSEPR diagram, and I can draw the lone pairs, but because the dispersion of these electrons is symmetrical, the lone pairs don't change the polarity of the molecule, and carbon dioxide or any linear VSEPR diagram is nonpolar. So linear VSEPR diagram is 2 atoms bonded to the central atom with no lone pairs on the central atom. Throughout this video, when we talk about lone pairs, in this table, I'm going to be referring to lone pairs on only the central atom. Okay, so now let's move on to trigonal planar with BH3. So I have boron and 3 hydrogens. Boron has 3 valence electrons. Each hydrogen has 1. These are all going to be bonded together. And remember, boron is electron deficient, so it can have less than 8 electrons in the valence shell and still be stable. So BH3 has 3 atoms bonded to the central atom and no lone pairs on the central atom. So we are going to draw the VSEPR diagram. You can draw these diagrams in different ways based on how you're looking at the 3-dimensional figure. I'm just going to draw it the way I normally do. But in my AP Chem version, I'll probably draw it slightly differently. So with 1 wedge going out, 1 wedge going in, and 1 flat wedge like that. And trigonal planar VSEPR diagrams are nonpolar. Next, we have CH4. So I'm going to draw the VSEPR diagram. A single bond between each carbon and hydrogen to make a final Lewis structure that looks like this. Okay, so this one has 4 atoms bonded to the central atom, and the central atom has no lone pairs. This is called a tetrahedral VSEPR diagram. So the way I'm going to draw it is with 1 flat wedge, 1 coming out this way, 1 coming out this way, and 1 going back into the page here. And this one is also nonpolar. Next, we have NH3. This is trigonal pyramidal. And I'm going to draw that out. So nitrogen has 5 valence electrons. Hydrogen has 1. So this will be a single bond from nitrogen to each hydrogen. And there is 1 lone pair on nitrogen. So the trigonal pyramidal VSEPR diagram has 3 atoms bonded to the central atom and 1 lone pair on the central atom. So I'm going to draw it like this. We have a flat wedge, a wedge coming outwards, and 1 going back into the page. Each one of these has a hydrogen, and the nitrogen has 1 lone pair on top. So this is our first polar VSEPR diagram because of the lone pairs. Now you'll learn in AP Chem that's not always true. There is a VSEPR diagram with lone pairs on it that is nonpolar, but it's for a reason I'll discuss in another video. So keep in mind that these are 3D diagrams of the molecules. So the wedges coming out and in, those are to make the diagram seem as 3D as possible, even though we're only drawing them on paper. So next we have bent, and a good example of this one is water or H2O. So I'm going to draw the Lewis structure. Oxygen single bonds with each hydrogen, and the Lewis structure is drawn like this, and oxygen has 2 lone pairs. So say it with me, there are 2 atoms bonded to the central atom and 2 lone pairs on the central atom. So that gives us bent. I'm going to draw it like this. And the lone pairs are going to be together up there. And this is also a polar VSEPR diagram. Okay, 2 more. We have PCl5 or phosphorus pentachloride. So I'm going to draw this diagram. Remember, phosphorus is can have an expanded octet, 4, 5. Each chlorine has 7. And each phosphorus is going to bond 1 time with the chlorines. And I'm going to redraw it just to make it a little neater. And the phosphorus does not have any lone pairs, but each chlorine has 3 lone pairs. And so we have trigonal bipyramidal, that is 5 atoms bonded to the central atom with no lone pairs on the central atom. I'm going to draw it like this. So I have 3 flat wedges, 1 wedge coming out, 1 wedge going into the paper, and this is a non-polar VSEPR diagram. Next, we have octahedral. So I'm going to draw sulfur hexafluoride. Sulfur has 6 valence electrons, each fluoride has 7. And each fluoride is going to bond once with the sulfur. And remember, sulfur can have an expanded octet. So that would then look like this. So we have a sulfur with 6 fluorides. The fluorides have 3 lone pairs, but the sulfur, which is bonded to 6 atoms, does not have any lone pairs and is therefore nonpolar. The compound is therefore nonpolar. So we're going to draw the VSEPR diagram like this. We have 2 flat wedges, 2 wedges going into the paper, and 2 coming out. And these drawings don't have to be perfect. And like I said, you can draw them from different perspectives, but this is just how I'm showing mine. Just make sure if you're going to draw it differently than your teacher teaches you, that you're still drawing it correctly. So those are all the VSEPR diagrams I am going to go over. Okay, so as I was making the different VSEPR diagrams, I kept saying flat wedge, going out wedge, going into, stuff like that. And I just wanted to show you with the different kinds of wedges looked like. As I mentioned multiple times, the VSEPR diagrams are 3D, and therefore you can't have just flat lines like a Lewis structure because that's not a 3D diagram. These flat wedges just show a flat bond, and the wedges going outwards show a bond that's coming out of the page, and the wedges that are going inwards with the dashed lines show wedges that are show bonds that are going into the page. So VSEPR determines the polarity of not a bond, but a whole molecule. So, and as you saw with the different diagrams, some of these diagrams are polar, some are non-polar. Molecules that are symmetrical are non-polar, and a molecule that is asymmetric will be polar. So for instance, the bent VSEPR diagram is not symmetrical because of the electrons it has. So that makes the arrangement not symmetrical, and therefore makes it polar. Same with trigonal pyramidal. If you compare it to trigonal planar, you see that in trigonal planar, the different atoms bonded to the central atom are much more evenly spaced out. But because of the lone pair on the trigonal pyramidal VSEPR diagrams, the molecule is polar because it is no longer symmetrical. And you can also test if a molecule is polar or not if you don't know exactly what it is. If you mix a substance with another substance of a known polarity, you can determine if it's polar or not, because two polar substances will be miscible and two nonpolar substances will also be miscible. And miscible means that they will dissolve each other. However, a polar and a nonpolar substance will be immiscible, which means they will not dissolve each other. So just generally like dissolves like. So let's say you had water that you know is polar and some other molecule that you just had that you didn't know if it was polar or not. You could pour it in to the water, and if the two dissolved each other, then you would know that that molecule is polar. So now we are going to do some practice identifying the VSEPR shape. So we're going to start with silicon tetraiodide. So I'm going to start by drawing the Lewis structure. I'm not going to draw the circles. I'm just going to draw the bonds. So silicon is bonded has 4 bonds. So there are 4 atoms bonded to the central atom. Each iodine has 3 lone pairs. But because silicon has 4 valence electrons, it has no lone pairs. Therefore, with 4 atoms bonded to the central atom and no lone pairs on the central atom, we have tetrahedral. So I'm going to draw that. I'm no Van Gogh. I just try my best with these diagrams. So this is how we would draw tetrahedral, and it is non-polar. So boron has 3 valence electrons. Astatine has 7. So boron is going to bond once with each astatine, and each astatine has 3 lone pairs. So this is 3 atoms bonded to the central atom with no lone pairs on the central atom. This is going to be trigonal planar. So we're going to draw that out. And make sure you're drawing the lone pairs on the atoms bonded to the central atom. And this is non-polar. Next, we have SBr6. Each sulfur bonds once to the bromine, and each bromine has 3 lone pairs. So this is octahedral because there are 6 atoms bonded to the central atom and no lone pairs on the central atom. So let's now draw this out. And this is the octahedral VSEPR diagram, and we know it is non-polar. We know it's non-polar because it's symmetrical.
So I hope you enjoyed this video on VSEPR diagrams at the Honors Chem level. Next week, I'm going to be diving into the new unit about compounds, and I'm going to start with classification of matter. So if you need help with that, you are welcome to join me back next week. I'm going to put a link in the description box to my website if you would like to schedule tutoring. And if you have any questions, feel free to leave them in the comments, and I will do my best to answer them. I hope you enjoyed, and good luck with learning the rest of your chemistry.